Thanks, Kavian, and welcome everybody, and thank you for joining our webinar on the exhilarating topic of the evaluating high voltage insulators, and more specifically, this presentation delves into the results of a synthesized analysis of aging assessments on ceramic insulators which were returned from service. So let's have a quick overview of today's presentation. The agenda includes providing some background into the study, as well as the analysis itself. After reviewing the results of the synthesis, we'll move on to discussions based on the results and focused on some of the industry's anticipated challenges. This includes asset management and the totex of building and operating transmission lines, and finally, standards and insulator string designs. The overall objective of this webinar is to help the audience develop a deeper understanding of the performance trends of ceramic insulators, defined today by the industry standards to include both porcelain and toughened glass. Specifically, the study's goal is to better understand both materials as they age while in service. Now, armed with this data, the industry may elect to revise product or design standards that may lead to enhanced optimization. We also hope that this presentation provides info to asset managers, which allows them to allocate their efforts in the most efficient manner. The study's objective is pretty simple. Settlers often supported utilities in conducting aging assessments of in-service porcelain and toughened glass insulators, right? This is sometimes performed as part of an investigation after a failure has occurred or before undertaking the refurbishment of an old line where insulators are commonly replaced. But these types of studies are generally focused on a single population of insulators, and that's attesting to the statistical probability of failure across large quantities of insulators derived from a small number of samples removed from service and then subjected to lab tests. But this study is different in that rather than analyzing results from a single population, we endeavored to compile data from many assessments in the hopes of better understanding performance trends. Specifically, our interest was on the aging of the two types of ceramic dielectrics used in high voltage insulators today. The ambitious nature of the study required sending our archivist on a bit of a daunting quest, delving deep in our files, armed with nothing more than a dust mask to combat against the decades of cobwebs that were guarding the ancient test reports. But upon his safe return from the dark pits of our filing room, we compiled the results from dozens of assessments into a single synthesis that now had over 2,000 individual ceramic insulator samples. Now, before we move on to the study itself, I want to give you guys a bit of background on these aging assessments from which the synthesis is compiled. It's been well understood going back many years across much of the industry's literature how beneficial it is for utilities to understand the in situ performance of insulators, because it allows asset managers to better quantify the risks associated with maintaining a particular asset in service. By removing samples of a given population from service, Weibull end-of-life calculations can be performed following lab tests, but the difficulty arises in conducting this sort of analysis on larger populations of insulators. And again, there's much published on this particular topic. Seagray's guide for the assessment of porcelain and glass transmission insulators, it's just one example. Well, it suggests several tests, including galvanizing measurements, which quantify the remaining thickness of protective zinc on the metal components. It suggests visual inspections, residual strength tests, and some puncture tests. And they can all provide useful insight into the conditional performance of those insulators and populations from which they came from. But the most insightful test is the electrical mechanical failing load test, at least in my opinion. In this graph, we have the results from precisely that test, and it's extracted from an aging assessment that Setiver was asked to conduct several years ago by a Canadian utility. These were insulators that came from the 1960s, the late 1960s, when this utility decided to build a brand new 735 kV line at the time. And in fact, they were leftover construction spares. They were never installed, so they'd never been subjected to electrical or mechanical stresses, but they were left in outdoor storage going all the way back to 1967. So they had been subjected to the thermal stresses of the summers and winters, right? Those hot summer days and cold winter nights. And they had hoped, utility had hoped that they could use these insulators as part of their refurbishment project that they had planned for that line, where they anticipated replacing all the insulators. But before they went ahead and used these, they sent them to our lab. And as you can see here in the graph, where the green horizontal line represents 120 kilonewtons, which happens to be the insulator population's M&E rating here, any dots that fall below it, any blue dots that fall below it, failed to meet their rating. The dots above it passed, but the data suggests a fairly significant and advanced rate of aging of those porcelain dielectrics. And that's simply from the thermal stresses of the hot summer days and cold winter nights, like I said earlier. That was enough to convince the utility not to use these in their refurbishment project. So now, with our archivist having survived his quest, and we found ourselves with these 2,000 data points all compiled in a single synthesis, we had the results from 13 manufacturers in total, 7 porcelain, 6 toughened glass manufacturers. The samples included in the synthesis fall across a broad spectrum in terms of years in service, some having served only a single year in service before they were sent to us, while others were removed from service after an impressive 100 years, manufactured right at the end of World War I. To be included in the study, the insulators had to have been subjected to an electrical mechanical failing load test. I'll get into that a little bit later on. And the test results were then all normalized in terms of a percentage of each insulator's M&E rating. As previously mentioned, this study's primary interest was to better understand the aging of ceramic dielectrics, and this includes both porcelain and toughened glass. All samples were cap and pin type insulators removed from service. I think I've said that a couple times now. The samples ranged from fairly small insulators, 50 kilonewton, equivalent to about 11 kip, all the way to 400 kilonewtons or 90,000 pounds. They were installed across a wide range of voltage classes and applications, including both dead ends and suspension strings, applications with high loads, some with lower loads. And we included samples from a variety of operating conditions, given that we received these from utilities from across the globe. Though we aimed to cast a wide net in order to include as many samples in our synthesis as possible, we eliminated any sample that exhibited severe corrosion or wear that had the potential to compromise mechanical strength. And this allowed us to better focus on the aging behavior of the dielectric. Moving on to the testing itself, though it's referred to as the electrical mechanical failing load test by both IEC 60383-1 and CSA C411.1-16, ANSI C292B calls it the combined mechanical and electrical strength test, but fundamentally they're the same. It's a destructive test in which a tensile load is applied to the insulator until failure. Simultaneously, a minimum of 75% of the insulator's dry power frequency flashover voltage is applied to help identify electrical punctures in porcelain dielectrics. This is necessary as hidden internal defects within porcelain may remain undetectable outside lab settings and can mask puncture channels, through which current may pass, effectively negating the inherent purpose of the insulator, right? But due to the material properties of toughened glass, where the dielectric can only exist in either two well-defined states, fully intact or completely shattered, The electrical portion is not required by the industry standards for toughened glass. But no matter the dielectric material, upon the insulator's failure, mechanical and electrical failure loads are annotated along with details of the failure mode, right? For example, noting whether the failure occurred first on the pin, right, resulting in a mechanical failure. This test, this electrical mechanical failing load test, is required as both a type test, which is intended to validate new designs, as well as a quality conformance test intended to validate the quality of production and part of sample testing. Here's a photo of one of the M&E machines used in the study. And because there's an electrical portion that's required on porcelain samples, our machine must also be insulated, and to this purpose, there's that very large insulator at the top of the machine. In fact, it's below that insulator, that smaller one with the yellow band on the cap, that's the test specimen here. And for your knowledge, that's a 140 kilonewton insulator. It gives an idea of how large the one above it is. And finally, here is, in this slide, the results of the synthesis. Porcelain samples are represented in blue, while toughened glass samples are shown in orange. The red horizontal line represents 100% of the insulator's electrical mechanical rating, while the horizontal axis represents the years in service for each population, of which there are more than 60. Any data points below the red line failed to meet their electrical mechanical rating. Trends become apparent with toughened glass representing approximately 1% of the study's total samples that failed to pass their M&E rate, and then normalized across the study, given that there are a larger quantity of porcelain insulators. This approximates to about 3% of the total failures below 100% of the electrical mechanical rating. You see much fewer orange dots below that red line. And here again, we have the 2,000 plus data points, though this time the horizontal axis represents simply each individual sample number for each individual insulator included in the study, right? It's just kind of the study number for that sample. We've also colored the data points in a manner where each of the manufacturers included in the synthesis are represented by a unique color. And again, the red horizontal line represents 100% of the insulator's M&E rating. All the points falling below that have failed to meet their intended design load. Here again, trends become self-evident, with certain manufacturers clearly outperforming others. More granularly, we see certain manufacturers fluctuating in terms of performance across manufacturing periods, where certain eras outperform others, without necessarily there being a correlation to the years in service. Other manufacturers show more steady trends, both negative and positive, with some failures are rare, and with others, failures below rating appear more often. The same data is shown here, but this time ignoring manufacturers and favoring to compare porcelain and glass. Again, porcelain, as in that first slide or 2 slides ago, porcelain is shown in blue, toughened glass is shown in orange. Our now famous red line continues to represent 100% of the insulator's M&E rating, and all data points falling below failing to meet their design rating. Interestingly, here we see that regardless of the manufacturer, no toughened glass insulator failed below 88% of its electrical mechanical rating. Once more, it should be noted that as in the previous slide, the horizontal axis represents only the individual sample number and isn't representative of the years in service. Now, analyzing the results from the over 1,500 porcelain electrical mechanical failing load tests that were included in the study, there was a total failure rate of less than 1% noticed for units with less than 20 years in service. But beyond that, the failure rate climbed at a rate which resulted in about a 50% failure rate after 45 years in service. This, along with the fact that the majority of failures were attributed to the dielectric itself, is evidence of the aging of the porcelain body. This aging phenomenon is well documented, and it's understood to occur to a varying degree based strongly on the composition of the porcelain, right? As it's an aggregate of various minerals such as feldspar, quartz, silica, or microvoids and imperfections between the various mix of ingredients can propagate into puncture channels across the entire dielectric body. And that's with the introduction of either mechanical or even just thermal stresses, as we saw with those 45-year-old samples that were left outdoors. And here we have a magnified view of a porcelain dielectric. Why does this happen, though? Because the porcelain itself has a coefficient of thermal expansion that differs from that of the cast iron and the steel and the cement used in the manufacturing of the insulator. And while toughened glass benefits from a closer alignment to the expansion factors of the insulator's other components, porcelain's confinement within a cast iron cap, while a steel pin further restricts its ability to expand and contract without interference, results in mechanical strain within the porcelain dielectric. It's precisely these stresses that age porcelain insulators, though the tighter controls on the shape and size of those aggregates can mitigate with higher uniformity, resulting in slower degrees of aging. Now, in contrast, over the more than 500 toughened glass samples that were included in the study, there was a total failure rate of about 1% determined across 90 years of service. Unlike porcelain, where failures occurred predominantly with the dielectric, with the toughened glass insulators, there were no dielectric failures, and all the failures were attributed to the metal components. This is interesting in that, at least for what concerns some manufacturers, the metal component failures are often the intended failure mode, where the insulator is designed in a manner where the pin, for example, acts as a mechanical fuse when pulled beyond rating. But as can be seen here in the picture of toughened glass magnified 1,000 times, unlike the porcelain in the preceding slide, here there's no aggregate of minerals. Glass is amorphous and homogeneous in composition. As such, there's no possibility of aging of the dielectric with the introduction of either thermal or mechanical stresses, and this is in contrast to the porcelain susceptibility. It's precisely for this reason that toughened glass is often marketed as ageless. So, summarizing the synthesis, we notice good performance of both technologies for the first 20 years in service. But beyond that, porcelain insulators can begin to exhibit aging, eventually achieving a 50% failure rate after 45 years in service. There's no such aging noticed with toughened glass. The typical failure of the porcelain insulator was of the dielectric body or the cement, but there was no such failure with the glass. These were limited strictly to the metal components. With porcelain, failures were noted below 65% of the insulator's M&E rating, but there were no failures on toughened glass insulators below 88%. Moving on to discussion. In terms of the anticipated challenges, there's been much written on the Herculean demand for new transmission lines that are forecasted as necessary within the next few years. With tens of millions of kilometers of new lines projected to be built within the next 15 years alone, already there are anticipations of labor and material shortage in our industry. Now, without compromising quality, it'll be difficult for the industry to adapt to this new reality without accepting higher levels of operational risk. One way this is achievable, though, is through smarter allocations of the few resources available, whether those are human or material. looking in terms of the asset management and TOTEX and how this type of study can aid in those areas. Insulators, regardless of the dielectric material, represent a small fraction of the total cost associated with the construction of new transmission lines. And though the insulators may represent a small proportion of the capital expenditure or CapEx of building the line, in terms of maintenance costs, maintenance issues related to insulators can represent up to 50% of the OPEX or operational expenditures of operating that same line. These operational costs can dwarf the 5 to 7% of the CapEx allocated to insulators, resulting in a higher total expenditure or TOTEX to build and operate transmission lines. Now going back to the units left in outdoor storage, had the utility purchased toughened glass insulators in 1967, after looking at the results of the synthesis, in all probability, an aging assessment would have proven that those insulators, if they had been toughened glass, would have been still in good performing condition, and it would have negated the need for an expensive multi-year refurbishment. The funds and crews dedicated to that refurbishment could have been used towards the construction of new lines. Inspection costs can also be better controlled by better understanding which assets are more prone to aging and when, without assuming any additional operational risk. In terms of standards and designs, due to the similarities in basic componentry between porcelain and toughened glass insulators, many standards today govern them jointly. Clear performance trends exist differentiating the two ceramic insulator types, and given the differences in results between the two materials that we saw in the synthesis, it may be in the industry's best interest to question the continued parallel management. Today, permissible design loading and redundancies in design take into account the failure modes of both ceramic insulator types, as though they are one. If designing in accordance with 50% max design load, such as when designing in accordance with ANSI, CSA, I should say, you'll note the vast majority of failures occur above this, with only 1% of all samples failing below. But increasing the permissible max design loading to 65%, as when designing in accordance with NESC, this increases threefold the likelihood of encountering a porcelain insulator failure. Designs which consider separately the two insulator technologies benefit from an anticipated longer service life when choosing toughened glass, and can take advantage of the unique characteristics of this insulating material, such as higher average failing loads when compared to porcelain. This, along with asset management focused where limited resources are most needed, helps utilities maintain the lowest possible TOTEX on high voltage transmission lines. It should be noted that along with the differences between the two respective insulating materials included in this study, important differences were also noted amongst the manufacturers, with some consistently outperforming their competition. Should a utility decide to truly optimize, designs may include the use of fewer insulators across the entirety of new line to compensate for possible future material shortages through opportunities arising with these manufacturers who can prove through a synthesis that their insulators fail with failure loads exceeding not only 88% of their M&E rating, but consistently above 100% of their rating. No, that was not quite the 45 minutes that Karine had promised you, but I hope that this was informative nonetheless.
It was.
All right, perfect.
Okay, thank you so much, Alex. Here is just a little slide, the usual slide to present SETI, where you know us have the main manufacturer for toughened glass insulator, even if we can discuss about composite or porcelain, because we got a huge R&D center and a lot of different manufacturing factory, but also laboratories. So we running tests all around the world. That is why we have the possibility today to discuss this kind of topics. Thank you so much, Alex, for your presentation. It was really clear, and I think we got 3 questions for you. If you may, I will ask these question, and then if you need your presentation to show some results or detailed and answer, it will be easier if you continue to share your screen like that.
Absolutely.
The first one is how far back do the assessment included in the synthesis go?
So I think we went back 20 years or so. I think the first assessment included in the synthesis dates to about 2003.
Okay, and the M&E test is always the same since 20 years?
More or less, yes.
Okay, okay. So we can compare the results. Okay, great.
Exactly.
And the second question is, do you have data for glass similar to the example you gave on porcelain left outdoors for 45 years or more?
Off the top of my head, I can't recall 45-year-old glass that was left outdoors, but there are some examples of 25 to 30-year-old glass that was left in outdoor storage, and they tested as though they were brand new. There wasn't any degradation in performance noted whatsoever. And so long as they're not left in a corrosive environment, and there's a compromising of the metal components strength. There's really no aging of the dielectric that's noticed.
And you can handle this insulator as usual. It's not you don't need any precaution or whatever because they are as new.
That's it. That's right.
Okay, clear. Thank you. And the last question for you today is, were increases failure rates noticed on fog type insulators since they contain more dielectric material, or
We
something
didn't
else?
we didn't look into it at that level. We didn't separate or distinguish between the different dielectric profiles. It may be an area that we want to focus on, perhaps in a further study on the topic. It would be very interesting to find out.
Yeah, you're right, because of course the pollution can have a huge impact even if the toughened glass is not aging. It can be interesting to look for this.
Or even the fact that there's simply more dielectric material, perhaps the more included in an insulator, the more likely it is to age more rapidly.
Clear. And you, just one question, but it's mine, so sorry if it's not a good one. Do you know if this kind of assessment and study exists on composite insulator?
Not to my knowledge, and now it's about the second or third time I've been asked the same question, so perhaps that should be next, trying to conduct a synthesis of polymer assessments to better understand if we can see clear performance trends there as well.
Okay, and I have just one last question popping up right now about, do you have also reference to the behavior of porcelain long rod type insulators? Because for example, in service performance of German utilities show excellent aging behavior with almost no reduction of mechanical performance even after decades of in-service. Apparently there is a German Lakey study about that.
I know the C-grade guide that I referenced earlier does include how to perform that insulator type, assessments on that insulator type. But this study strictly focused on cap and pin suspension ceramic insulators, and really more in terms of a comparative study to understand, as I mentioned earlier, should they still remain managed in parallel as though they are one and the same, with very few exceptions to separate the two dielectric materials. I think it's an area that there's a lot more to learn. There's a lot more that can be undertaken in terms of the science to better understand insulators, regardless of the type, especially as we enter an era where, as I mentioned, there's possible material shortage around the corner. We may have to conduct asset management differently, whereas perhaps in the past we would have looked to have replaced certain insulators. In the future, we may elect to keep them in service because the availability of replacements is difficult.
Clear. And I think I got just one last question for you today. Interesting one. Manufacturing and quality control processes will have improved over decades. Are newer insulators aging better than the older insulators?
No, it doesn't seem to be. It seems fairly consistent in terms of the aging of the dielectric bodies. What I've noticed really is more trends from one manufacturer to another. There are some manufacturers of porcelain whose porcelain performs quite well despite being having many decades in service, while others it fluctuates. It truly fluctuates. There are some periods where they seem to perform better, other periods where quality perhaps wasn't quite the same. Yes, the standards have evolved. For example, the M&E acceptance criteria years ago was 1.8 sigma. ANSI today it's 3 sigma. CSA is 4 sigma. Nonetheless, the performance trends seem completely ignorant of these changes in the standards, and it's really more, I think, something that's directly linked to the material science itself. It's the material that, unless you've really mastered as a manufacturer the process, as I mentioned, the tighter controls they have in certain regards in the porcelain manufacturing. And I think the same can be said of glass as well, because there were performance trends that could be seen between all glass manufacturers, despite the fact that proportionally they performed better than the porcelain insulators. There were clear differences. So I think as we understand more of the science behind the two dielectric materials and how they break down or not with time and service, exposure to certain stresses, we can now also focus perhaps on the differences, the qualitative differences between the manufacturers, in order to ensure that only the very best insulators wind their way up in service, because I think there's enough data to prove now that you can put the very best insulators up into service, and that investment will pay dividends long term in terms of reducing your operational costs, your maintenance costs throughout the course of the transmission line's life.
Thank you, Alex. Yeah, it will be it for today. It was the last question for us today, for you, because not for me, obviously. So thank you so much for sharing all these results today. It was very interesting and clear. And if someone has another question, don't hesitate to drop us an email on info@cediver.com, and of course, don't hesitate to follow us on LinkedIn and our website to stay up to date and be aware when we will do another session of our technical webinar. Thank you all for coming and joining today, and thank you, Alex, again for your really good presentation.
My pleasure. Thank you.
Thank you.
Take care.